All right, I want to show you 37 problems that all citizens should know. Let's take a look.
Compute the total cost per year of the following expenses. Now, one thing that's very important is to be able to put your expenses on a common time frame. So, for example, in this example, we're spending $22 every week on coffee and $136 per month on food. Well, those are different time frames. So even though it sounds like we spend a lot more money on food than we do on coffee, one's in as a week, one's per month. So what we're going to do is we want to scale those to the same time scale. The question says over the course of a year, so we're going to go ahead and scale both of them. We're going to take into account that there are 52 weeks per year and 12 months per year. And we're going to use those facts to scale those up. So $22 every week means 22 times 52 would tell me how much per year, and 136 per month means I'm going to do 136 times 12. When I multiply those out, now I'm comparing the same time scales. They're both per year. So now when I compare it, I can go actually subtract and find out how much more am I spending on food than coffee. And so in this case, I'm spending $488 more on food than coffee per year. Now that we have it in the same time scale, it makes it a lot easier to compare.
All right, so in this one, we're going to find the monthly interest payment on a credit card. And I don't want you to overthink this one. So in this case, you have an average balance of $950 on your credit card. And if you don't pay it all off and you carry that balance, you have to pay interest every month. You have to pay your finance charge. And if the interest rate on your credit card is 18%, then you can take that $950 balance and that 18% interest rate. You need to make it into a monthly interest rate. So we're going to divide it by 12. So it's like 1.5% per month. Then we're going to multiply that by our balance to get our monthly interest. So we'd end up with $14.25 for our finance charge this month.
Now, when we're talking about interest, we can have good interest, interest in savings accounts, but we can also have bad interest. In other words, the interest on purchases, for example, in a credit card, or if we finance a purchase and we buy something on credit. For example, if Vic bought a new plasma TV for $2,300, he got a nice TV, and then he went to the cash register and they said, would you like to actually only pay $100 today and then finance the rest at 0% financing? You just got to pay every month and pay it down, and there's no interest or anything. You just get free delay in paying it back. Now, if Vic takes this deal, which he did, and then makes the mistake of forgetting a payment. In this case, Vic forgot about this monthly payment and did not pay his first payment. And a lot of times when you make these financing agreements, even on a credit card, if you miss a payment, they actually will raise the interest rate. So Vic ends up having to pay a 5% interest per month on the balance every month so that he can pay back that privilege of not paying it all up front. So his upfront cost was $2,300. How much is he paying every month in interest? Well, we need to first account for the fact that he did pay $100 off, so he only financed $2,200. And 5% of that $2,200 is going to be his monthly interest, his finance charge. So he's paying $110 a month just in interest. So even if he pays $110 every month, after a year, he'll have paid quite a bit of money, but he'll still owe $2,200 because that's just the interest. When you're deciding your cash flow and taking into account your monthly expenses, you need to remember that you don't pay all your bills every month. What I mean by that is some things you only pay every 6 months or every other month. So in this example, we have land paying a semi-annual premium. That means that land is paying their semi-annual premium every 6 months, twice a year. Also have a monthly premium for health insurance and an annual premium for life insurance. So those are all on 3 different time scales. So if we're going to calculate our monthly expenses, we're going to want to scale each of those to find the average cost per month. First, we have the $700 big automobile insurance, but that's every 6 months. We have the monthly premium that we do pay every month, and then the annual premium that we pay every 12 months. We're going to scale it down and divide each of them by the number of months so that we then match our terms. And so when we go ahead and divide each one by the number of months, it gives us an average for each month for each expense, giving us a total of $324.17. Now, when you're making a budget, whether it be personally or for a business, we might call that a cash flow. We want to figure out how much money is coming in each month, income, and how much money we're spending each month in expenses. And so for this example, we notice that we have a couple sources of income and we have a bunch of expenses we have to figure out. And the key to doing a monthly cash flow is to include things that don't necessarily have, for example, one cost per month. Like groceries, you might buy groceries every week, so you need to account for that multiple times. Some things you won't pay every month, like car insurance, you might only pay twice a year, so you need to scale that down to fit the appropriate time frame. For this one, we're going to assume that 1 month is 4 weeks, just to simplify our math a little bit. We have our income as a salary, plus we have some extra sales that we sell for pottery. And so we're going to find that net monthly cash flow by first finding the average monthly income from each of those sources. So the monthly income being, well, we're going to take that yearly salary and divide it by 12. And then the pottery sales is already in a month, so we're just going to say plus 196. Our monthly expenses we have to pay close attention to, because for each line we need to pay attention to whether we pay it once a month, whether we need to count for it 4 times because it's weekly, or whether we're going to count for it multiple months and we have to scale it down. For example, donation says $660 a year, so we need to divide that by 12 to make that work. If we do run all the numbers, we end up with $2,418.33, which means we actually spend less than we make. That's great news. It means we're going to have a positive cash flow. Actually, we have extra $719.34 in that cash flow that we get to figure out where we're going to spend that.
All right, so we have some data here. We have this percentage of spending by category in each age group. And we see certain things like there's a trend that as you get older, you spend more on your healthcare and you probably spend less on clothing as you get older. And if we look at this situation, we say, is this normal for a 30-year-old woman to have spending $1,460 on rent if she has a monthly salary of $4,300? So we can calculate this, compare it to the graph that we have, and see if she's normal or if she spends more or less than a typical person. So we've got this category. We can take her spending, divide it by her total, and that gives us the decimal 0.3395, but we're going to want to turn that into a percent. So we're going to multiply by 100, and then we're going to go ahead and round it to just one decimal place. Now notice this one ends up kind of funky because it's 33.95, and if I only have one decimal place, that 9 becomes a 10, so it ends up being 34.0. Now if we look right here, we can see, well, guess what? As far as housing goes, housing, 34.0 is average, so she's spending pretty normal amount. Comparing a couple that is a young couple under the age of 30, and they have a household income of $3,100, so not a lot of money, and they spend $229 per month on entertainment. Is that a lot? It doesn't feel like a lot, but let's put it in context of their income. So if we go ahead and divide their spending by their total income, we get 0.0739. If we turn that into percent, we end up with 7.4% because that 39 makes it round up to 7.4. And if we look in our table, in our graph here, it says entertainment for young people is about 5.0%. So they actually spend above average. They spend more than average. So they might want to cut back on their entertainment spending, or just, maybe that's how they want to spend their money. All right, you've always got to weigh your options. We've got two job opportunities here. We've got a part-time job. It pays better per hour. It pays $18 per hour, but we're only going to have 21 hours to work. So good and bad. But if we multiply that out, we'd end up with an income of $378. But if we take the full-time offer we have a full-time job offer of 40 hours per week at only $14 per hour. Now, because it pays less, are we going to make less money? No, because we're working about twice as much. So we end up making more money. We end up making $680. So it is more, obviously, if we're going to work twice as much. But there's an other part of this. The other part is it says if you have all the extra free time because you're only working part-time, you actually found that you're going to spend more money on entertainment. You're going to have some free time, so you're going to spend more money. So we got to factor that into our cash flow. So we have the $378 in income if we work part-time, but we have $90 in expenses. For working full-time, there's no entertainment expenses because we're too busy to spend money. So if we go ahead and figure out what our cash flow is, our part-time job, we'd only be making $288 once we subtract the $90 extra we'd be spending on expenses. And so our cash flow of $680, because we're not spending any money at our full-time job, means that we actually make about $392 more as far as cash flow in the full-time job. Now that's in this example. Make sure you weigh your options. Let's say you're going to take a college class. If you're going to take a college class, you got to pay for the tuition. So 3 credit hours. If you just paid $500 an hour, then we can calculate our cost at $1,500. But this says, hey, in order to take that, you're going to have to take time off work. And you normally get paid $15 per hour. So not only do you have to take into account the cost of the tuition, but we need to take into the fact that you're going to spend probably 9 hours per week on that class for 15 weeks. And that means $15 for every one of those hours over the whole semester that you're not going to be able to work because you're going to be busy doing schoolwork. That means there's $2,000 that you're not going to be able to make in income. So if we compare these two options, should you work or should you take another class? And we can see that if you take another class, not only do you have to pay for the class, but you're going to lose some money. So we actually end up having a net loss of cash of negative $35.25, or a net loss. So it's negative because it's lost, but we're going to lose $35.25. So the net cost of that is actually even more than just the cost of tuition because we've lost some income.
Calculate the amount of money you'll have at the end of an indicated time period. But here's the catch. In this problem, we're going to use simple interest. So if we invest $2,000 in an account and it only pays simple interest, that means every year we're going to get 2% of what we started with. Simple interest, you get interest only on what you started with. And so what we started with was $2,000. So to figure out our simple interest, we just multiply what we started with times our rate times our time. And so we'd say we made $800 in interest. However, that $800 ends up being just the profit. The question says, how much money will we have at the end? We're going to have $2,800 because we have to add the $2,000 we started with. Use the compound interest formula to determine the accumulated balance after the stated period. So let's try a few things on this one. So first we have the $8,000 invested. We have an APR of 8% and for 5 years. APR is annual. Okay. So they haven't told us how often we're going to compound this. So let's assume we're going to compound it annually. Okay. So we have the amount we started with, 8,000. And we're going to multiply it by 1 plus that 8%. And we're going to do that 5 times. So I'm going to put the 5 as an exponent. And what you'll get when you do this is, notice that 8% and that 1 look a little ugly when we do that. So I'm going to switch it to a single number to show you that what we have is 1.08. And as we multiply by 1.08 5 times, we're going to get a little bit more interest each time. And so if we were to plug that into our calculator, it would give us our compound interest compounded annually. Now, if we were to do investments in compounding interest, I'm going to be honest, I usually default to not doing that stuff by hand because I want to use a calculator that's going to take into all the stuff really easily. And for that, I use Microsoft Excel. You can use Google Sheets if you don't have Microsoft Excel. It's going to be the same formulas. Now there's three big ones we use in this scenario. One is the PV function. That's for the present value, or how much do I need to save now? How much do I put now? The FV function is how much will I have in the future? And then the PMT function is how much do I need to pay monthly or save monthly? Do I need to add a monthly amount to my account? So in this case, it says use the compound interest formula, and these all do compound interest formulas all automatically. These aren't simple interest. Determine the accumulated balance after the stated period. So my stated period is 5 years, and I need to know my future amount. So that's going to be my FV. And when you use Excel, it lays it out for you, and it gives you hints as you're typing it in. So I'd start by typing the equals FV and then the parentheses, and then it'll walk me through the rest. You can see I have to put my rate and then my number of periods, which is just, in this case, 5 years. I'm not making monthly payments in this case, so I'm going to put 0 for PMT. And then lastly, I'm going to put my PV, my present value, my lump sum that I have in the present, which is $8,000. When I put all that in, I can press enter, and it gives me my answer as $11,754.62. So if I put $8,000 invested at 8% for 5 years, compounded annually, it'll give me that result.
Now there's some vocab that you want to know in financial formulas, and you just got to be aware of them. So I'm going to give you a whole bunch of them real quick. But I want to first just make you aware, we use a lot of shorthand in formulas. We use A and P and Y and N, and even the letter E means something. And you can see what each one of those stands here, but there's also some swapped out terms. For example, A, sometimes we call that F or FV for future value, but it could be A for the accumulative balance. So just be aware that there's some mixed around terms. I do want to highlight, in this example, it says the blank in financial formulas is the balance upon which interest is paid. But what is the balance you pay interest on? Well, that's going to be not the accumulated balance, but that's going to be your principal. So we're going to go ahead and say the P, or the principal, is our balance upon which we pay interest.
Whenever we see evaluate, what that means is we're going to crunch the numbers. That's what evaluate means. And so in this case, all we have is numbers. There's no variables. So we're going to evaluate and simplify the expression. We should end up with just a single number. So following order of operations, you could try to type this all in your calculator. And I don't trust calculators all the time. If you've got a calculator you trust, then you could go ahead and type this whole thing in. However, what I would probably do here is I'd probably split and do the two parts separately. In other words, the 2 to the 4th power and the 4 to the 2nd power. And if I do both of those separately, well, they actually both end up being 16. So 16 plus 16, then I can do that math pretty quickly, 32. Okay, so evaluate just means we're going to crunch the numbers, but be careful we don't just trust whatever our calculator spits out. Evaluating this expression, we have something kind of scary. We have a fraction. And to make it a little bit scarier, we have a fraction as an exponent. Now, if you don't have a calculator that can do this, then you need to quit and pick a different calculator, okay? You want to have a calculator that can allow you to type whatever exponent you want. And so this one, you can type it as 1/2 or just 0.5 as a decimal. That's really the same thing as a square root. So when we say 1/2 power, that's like saying the square root. So this is actually the square root of 64, or just 8.
Let's not forget our solving equations. So here's a two-step equation. We have an x, and we have some other numbers in here. And our goal when we solve equations is to get the x by itself. So we're going to work through our order of operations, but we're kind of going to work backwards because we're going to try to peel stuff away until the x is all by itself. The x is not by itself for two reasons. The first thing we're going to do is we're going to go ahead and add 18 to both sides. So we're going to try to get rid of the 18 that's there, and it's a minus 18, so we're going to do the opposite. If you add 18 to both sides, you end up with 8x equals 64. Now the x is not by itself yet, but it's just got that 8. What is the 8 doing? The 8 is multiplying. So how do we get rid of multiply by 8? We divide both sides by 8. And when we do that, we just get x equals 8 because 64 divided by 8 is 8. And that ends up working out. So we always want to try to get our variable by itself. And we do that by taking each of the pieces that are on that same side with it, and we eliminate them by doing the opposite operation. If you want to have $90,000 in a college fund in 15 years, and you want to just start by depositing a lump sum now and let it grow for 15 years, how would we calculate how much we need now? So what we're going to do is we're going to look at our Excel formulas, and Excel will do a lot of these financial formulas a lot quicker than we could do them if we did them by hand. So we're going to use Excel. And the three big ones I use a lot in Excel for financial are PV, FV, and PMT. In this case, we want to know how much do we save now. So we're going to use our PV function. What we're going to plug into the PV function is we're going to plug in what it asks for. It asks for, one, the rate. And so we want to put the rate down as 5.7%. We can put percents in, or you could switch it to a decimal and do 0.057. But I want you to notice that since this is compounded daily, we have to divide by 365. If it was compounded monthly, we'd have to divide by 12. Notice for the number of periods, the N per, not only do we put the 15 for the 15 years, we also multiply by 365 so that we end up having, again, the compounded daily. We don't have any payments. It says we're not going to make any more deposits after the first. And we know that what we want for our future value is 90,000. So we'll put 90,000 in there. There's a type there, but you can leave that off. You don't need that. And we end up with, if we put $38,278.04, and we get that interest rate compounded daily for 15 years, it would grow from 38,000 to 90,000. How much must you deposit today if you want 100,000 in a college fund in 16 years? Assuming you're not going to make any additional deposits. And we might have done this before, but this one says quarterly compounding. So I wanted you to see what happens when we do quarterly compounding. But first, we're going to use Excel to do our prediction here. And it wants us to tell it how much we save now. How much are we depositing today? So I'm going to use PV. And what I'm going to plug in my formula is I'm going to put my rate, but I'm going to divide it by 4 because it says quarterly compounding. Now, quarterly means 4 times a year, which means I also need to take my years for an N per. Instead of just putting 16 for 16 years, I'm going to put 16 times 4. When we put that in, notice it says we're not going to make any more payments, so we'll put 0 in for payments, and we want 100,000. So that's what we'll put for the fourth thing for FB. Once we do that, we find out 38,000 would do it. 38,000 would grow to 100,000 if we just let it wait 16 years at that quarterly compounding. 4,000 is deposited into an account right now, and if we wait a long time, eventually we'll have $100,000. So the question is, how long do we have to wait? How long would we have to wait if we get 6.4% interest compounded annually for $4,000 to turn into $100,000? So how big of an increase is that? We're actually not going to use Excel to do this. There is a formula we could use in Excel, but I don't prefer it. So I want to first just talk about how big of an improvement is this. And so a couple of reference formulas I put down here in the bottom, but the big one is total return. What kind of return is to turn 4,000 to 100,000? Well, that's a big return. That's a 2,400% return. However, that means what we're taking is we're taking the 4,000 and we're multiplying 4,000 by 25 to get to 100,000. In order to do that, we only have 6.4% annually. And so we can use our logarithm formulas here to say log of 25 divided by log of 1 plus the annual. So we end up with 1.064. And then we say equals, and we get 51.89. Now, it actually does ask us to round up, which is good. So we're going to wait 52 years, and that'll turn $4,000 into $100,000 just with the power of compound interest. So if you want to find your savings plan balance in the future, we could use Excel to do this kind of math. And there's 3 main functions I use in Excel using compound interest. And so this one is obviously going to be the future balance. So I'm going to use FV for my future value. When I start typing in equals FV with the parentheses, then I can walk through each of the things that it needs, which first, it needs the rate. I'm going to type that in as 0.07, but you could actually type that in as 7% and use the percent symbol. But this says monthly payments. So we're making monthly payments. So
I need to switch my annual rate to a monthly rate. And so rather than just write 0.07, I need to divide it by 12. And so I get 0.07 divided by 12. And then I have 3 times 12 for my number of periods because, again, we're scaling it down to monthly. So I'm not just making 3 payments. If I'm making monthly payments for 3 years, I'm making 36 payments. And you could type in 36 there. I'd like to put 3 times 12 so I can keep track of where the numbers came from. Then when it says PMT, PMT is the payment made each period. And so in this case, it says I'm making monthly payments. I'm adding to my savings account $100 each month. And then I could keep going and I could say how much am I starting with is my next thing. But I am starting with nothing. So I'm going to leave it as just right here and I'm going to close it off. I'm not going to put anything for PV. If you want, you can put a 0 in there. And it calculates for me. It says that $100 a month after 3 years at 7% will add up to $3,993.01 in my bank account.
All right, this question is asking about making money on stocks. So if we buy shares of stock, you pay for each share you buy, and we bought 50 shares of a stock XYZ, and for each share, it cost $80. So all in all, we actually spent quite a bit of money. We spent $4,000 on this stock. However, taking that into consideration with what we sell it for, we actually made a profit. We made a 45% profit. However, that's over 5 years. So if we wanted to calculate our annual return, we need to do a little bit of funky math here. We got to do 1 over 5 as an exponent. So we have to get used to using exponents that are not just regular numbers like squared. What we end up with is, well, 0.077. So as a percent, we'd say, well, times 100, 7.7% annually. And so even though our purchase was just for $4,000, we sold it for $5,800, so we made money, about 45% return. But that's an annual return of 7.7. I want you to notice that if you multiply 5 times 7.7, you won't get 45. Because remember, if we compound our interest, we end up having that grow to a bigger number over the long term.
"17 years after purchasing shares in a mutual fund for $5,900, the shares are sold for $11,100. So that's a profit. But we don't want to just say we made money. We want to say, was it a good investment? What was our return rate in both our total return and our annual return? So let's start with the total return. Total return is kind of like percent change. We just take the amount we sold it for minus the amount we started with, and we divide it by the original amount, and then we multiply by 100 to turn it into a percent. That gives us the 88.1%. So that's a good return. That means we made 88.1% of our money on top of the money we started with. So we almost doubled our money. That's a good return. However, it's worth noticing that this did take 17 years. And so for 17 years, you had to wait for that to get to 88% profit. So another thing we got to look at is the annual return. The annual return means we're going to take how much we ended with, the amount we ended with, divided by the amount we started with, and then we're going to raise it to the 1 over y. And so in this case, 1 over 17 power, because we need to account for the number of years. And then we're going to subtract 1. And what happens when we do that is we get 0.038. Now, we do also want to multiply by 100, so we have it as a percent. So that means at an annual basis, since it took us 17 years, we actually only made 3.8% per year when we talk about the annual return. So it's important to look at both our total return and how much money we made, but also our annual return. And that really reveals whether the time it took for it to grow was worth it. One way you can evaluate stocks is with something called a PE ratio. So we have a PE ratio of 10.91. And this particular stock also had a price per share of $99.86. And so a PE ratio, the first thing we're going to do is, all right, we know the price. The PE ratio is actually the price divided by the earnings. And so we know price divided by earnings is 10.91. So we can actually figure out how many earnings there were per share by just plugging in our price that we have and then solving that for E by multiplying by E on both sides and dividing by that 10.91. We do that, we end up finding the earnings is about $9.15 per share. And so that company is making a profit. And this isn't a terrible earnings amount, but it's in the context of what the price of that stock was. So since that stock was priced at $99.86, that's a pretty low earnings for that price. In other words, when we look at the PE ratio, it takes into account the earnings and how high the stock is trading at. In this case, it's trading at 10.91 as a PE ratio. And so when we see that, we have to say, where's that normal? And so historically, this stock has a PE ratio between 12 and 14. So a PE ratio of 10.91 is actually low. It's actually an underpriced stock. And so that means it might be a good buy because the price is low considering the earnings based on the historical data.
Suppose you're a 25-year-old and would like to retire at age 65. You've got some time. And let's say you want to live pretty well. So according to this, it says you're going to have just a 3% return. We're being very conservative. However, we want $202,000 per year. So that's how much we want to take out every year out of our retirement. Now, the problem with that is if we keep taking money out of our retirement, won't our retirement run out? And if we plan it just right so that we only take out 3% and we're making 3% interest, then we'll never run out of money. It'll just be taking money that we're making each year and our balance will stay the same. So how much money do we have to have if we're only getting 3% return and we want to live on 202,000? To do that, we're going to just first find out what is 100%. If 3% is 202,874, what's 100%? What would our balance be? And our balance ends up being about 6.7 million. Now, that seems like a lot, but we're living pretty large. And we're using a pretty conservative 3% APR. So if we look at our future financial projection of 6.7 million, the question then becomes, how are we going to get there? Well, we've got 40 years. That's the good news. And so it says, how much would we have to save monthly? How much would we have to save monthly in order to have this amount of money? And so we are going to use our how much to save now, or we could say, I don't have enough money now to say I'm going to just put it in the bank. Let's put aside money every month from now until the time we finish. We're going to use our PMT function. And notice we use all of our normal things. This is compounded monthly, so I'm going to divide the rate by 12 and multiply the years by 12. But then I have that big number in my FV. Notice I put PV at 0 because I'm not starting with any savings. Let's just assume I plan on getting from 0 to 6.7 million just by making monthly payments and collecting a little bit of interest. Well, if that's my plan, it's going to cost me. It's going to cost me about $7,000 a month. So there's a few ways you can make more money in the long term. You can get better interest rate, you can wait longer, or you can start with more money. We want to real quick run through our calculations to predict a monthly payment on a home mortgage of $175,000. Notice we have a fixed APR of 4.5%, so that's not a bad interest rate, and we have it for the 30-year term. To calculate the monthly payment, I'm going to use Excel to do it because Excel is going to handle this calculation like a dream. Specifically, we're going to use the PMT function if we want to calculate payment, and we're going to put in everything it asks for in the order it asks for it. It asks for the rate, so we're going to put in the 4.5%, which is our interest rate, but since we're making monthly payments, not yearly payments, I'm going to divide it by 12 because that 4.5 is an annual interest rate. And then it wants the number of periods, so I'm going to put 30. But again, I'm going to multiply by 12 because I'm not just making 30 payments. I'm making a payment every month. So 30 times 12 or 360 payments. The third thing it needs is, well, what's our principal? What is the loan amount? Well, it says right there, our mortgage amount is $175,000, so that's what I put in for my PV. I left the rest off because let's assume the FV, our future value, we're going to pay the whole thing off. It's going to have a future value of 0. If I do that, it says my monthly payment, just including my bank costs, is $886.70 every month for 30 years, which isn't too bad. But I want you to notice that when you finance something, it doesn't sound too bad. But if we were to take that and figure out what our total amount we're paying, if we take that monthly payment and we're going to pay it every month, so 12 times a year for 30 years, if we multiply that all together, we're going to end up paying $319,000 to the bank. $319,000. Now, $319,000 is a lot more than $175,000. And so the reason the bank ends up giving us the money is because they make a bunch of money back in the long term. In fact, we can calculate how much money they end up making in profit. If we look at the 175 that we borrowed and notice that the 319 is a negative number because it's in red. So I'm actually going to add these numbers together instead of subtracting them. And we can see that, well, we're going to pay $144,000 in interest. That's the profit the bank is making on this deal. So if we wanted to put as a percentage, we could write those numbers as a fraction and then go ahead and multiply them by 100 or make them into a percent. We see that 45% is how much we're going to pay in interest, or 55% is how much we're going to pay towards the principal. And so we can do that math right there. We see that that would have to add up to 100%. I want you to know your sampling methods. I'm going to throw a bunch of sampling methods at you right here. I'm actually going to show you an example. Here's 5 examples: systematic, stratified, convenience, cluster, and simple random sampling. I want to give you just some examples. Systematic is when you have in every other, or in this case, every 10th shopper at a store on a Saturday, you might have a systematic sample like that. You're making sure you get a variety, but it's every 10th. So that doesn't mean you're getting a very definitive variety. Like, you're not going to get everybody if you get every 10th. And it's not random. Not really. Stratified sampling, you might not want it to be perfectly random, but you want to make sure you cover everybody. For example, if you want to take a sample of voters from each state to see who's going to win the next election, then you might pick voters from every state and make sure you include, like you might have a quota, make sure we survey 500 people from each state. And by doing that, it's not really random, is it? Because people in Iowa and people in Wyoming might have a greater likelihood of being sampled. Might be a greater likelihood because there's less people to choose from. So it's not really random. Convenient sampling just is what it sounds like. We just choose whoever's convenient to us. We might choose the people that are sitting next to us in the lunchroom, or the people closest to you at a bus stop. A cluster sample would be that we randomly pick a cluster. So we break them down into clusters. For example, if you pick from 100 schools, if you pick 100 schools at random from all the schools in the country, and then you gave a survey to all the teachers in all those 100 schools, that's going to be a lot of work, but it's a lot less work than trying to randomly get sample of teachers from all the schools in the country. So it's a little bit random, but it's a little bit convenient as well. Simple random sampling, that's the key. We want to try to do that as best as possible. That's when you literally randomly pick, like we're picking names from a hat. One easy way to do this is to go ahead and put everybody that you could pick in a spreadsheet and assign them a number, and then just randomly pick from that list of numbers. I want you to know about the types of data. Qualitative and quantitative data are my 2 big types of data. And the way you can think about it is quantitative data has a quantity or a number. Things like your score or the weight or your shoe size, those are all numerical data. And those are quantitative data. That's what quantitative means. It means they're a number and they're a quantity. Qualitative data are the things that are not numerical. For example, your eye color is something about you that is a characteristic of you. I could record it. It is a fact, and I could collect data on it, but that's not something I could collect data and then add all the eye colors together. Now, That is to say that there are times when you have qualitative data that is numerical. You can have a qualitative data point that's a number, but it's not really a number to make it quantitative. What do I mean by that? For example, let's say your address. If you lived at 123 Fake Street, that 123, is that a number about you? Yes. Is that a number you can do math with? Is that a number that it would make sense to take people's address and add all the numbers? No. So it's not quantitative data, it's qualitative data. Another one might be if you ask somebody's opinion on something, you're getting their qualitative opinion. Okay. So even if you said, rate this on a scale of 1 to 10, and you ask somebody their opinion, how well did you like the movie Inception? Rate this movie on 1 to 10. That number isn't quantitative data because it's an opinion. So that's another way you can kind of tell the difference between qualitative and quantitative. We have a very weird looking graph, but it's showing essentially a bar graph. It's actually a pictograph because we kind of have pictures involved. But it's showing us smoking comparison between male smokers, men and women, male and female. And what we can see is that smoking overall went down, and the gap actually changes each year. So in some years, it was more than others, the difference between men and women. But men seem to smoke more often than women. So when we look at those numbers, it actually asks us in this question, which year was it about 9 percentage points different? And what year was about 9 percentage points different? And we can look at these, and none of them are at 9%. If we want to look at it, we want to look at the difference between them. So when we look at the gap between them, we can kind of subtract and kind of guess how many percent is that. And that looks like about 8 to 10%. So that does look like about 9%. I want to look at this category. Well, that doesn't look like enough. That's not even 5%. And this is also not even 5%. So we would be able to say 1975 is the year that it was about 9% greater smoking percentage for men over women. We have this really interesting graph. Now, this is showing the percentage of utility bill. So if you pay your utilities, some months it's going to be more for your water, some months the electric's a bigger portion of what you're going to spend, but some months you might have natural gas as a greater expense. And so we're seeing this over the months January to June. And this question actually asks us for the month of April, which utility is at its greatest? So we first need to identify April would be the fourth month of the year. So if we look at the fourth column, it doesn't ask us which one is the biggest. It says which one of them is at its biggest. And if we look at the black bar in April, the black bar is bigger than it is in any other month, which means we're going to pick water. Water has reached its biggest percentage in April. What type of correlation do you see in this scatter diagram? Now, I kind of see a pattern here. They're not all perfectly in a straight line, but I can kind of see there's kind of like a trend. I would kind of draw a line. This kind of shows it, but you can see that they're not really strong. There's some points that are way off of that line. So I'm going to call this a weak positive correlation. Why is it positive? Because it's going up as I go from left to right. So it has a positive slope. What type of correlation do we see on this scatter plot? And if we look here, I definitely see a pattern. They're kind of going up. They're not a perfect straight line, but they're pretty good. In fact, I would say this is a strong correlation. They're all pretty close to that line. I can definitely tell it's going up. And so we have a strong positive correlation.